Ladies and gentlemen, welcome to the ICE technical meeting. To engineering aspect of the Merauke irrigation project. This event is brought to you by the Institution of Civil Engineering. My name is Muhammad Jikri and I am from ICE Student Chapter Binus University, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. Second, there will be opening remarks by the chairman of ICE-JLA Local Association, Philwood Mensi. After that, the event will be guided by David Meg as our moderator to start the presentation of Gogo Andre Benjamin and Kania Losiana. The event will then continue with a Q&A session. Ladies and gentlemen, for your own convenience, please pay attention to the following rules. You can submit your question for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. Now, I would like to invite the chairman of ICE-JLA Local Association, Philwood Mensi, to give his opening remarks. So Philwood Mensi, the time is yours.
Okay, thank you, Zikri, and welcome everyone to our ICE Jakarta Local Association presentation. We've got something a little bit different for you tonight in that it's a pleasure for us to welcome two fairly recent graduates, although I think they've been working for a couple of years now, graduates from Bandung, the Institute of Technology. So it's great that these guys have taken time to come and talk to us and to showcase their skills and to show how important it is to be able to present our projects, whether it's to an audience like this or to our clients. So the topic tonight is two engineering aspects of the Merauke irrigation project, which is in Papua, and it's almost on the Papua New Guinea border on the south coast there. So very much looking forward to listening to you guys. And I also would like to welcome David May, who is our ICE country representative. And I know he's been intimately involved in the project. So I think David's going to give an introduction and move on to our presentation from our speakers. So over to you, David. Thank you.
Can everyone hear me?
Yes, we can.
Everyone to the meeting, the graduates, members, and I think there are some invited guests. Let me just share my screen. Okay, can everyone see my presentation? I'll just
Yeah, we can see it, David.
I'm just looking to see where I get how I. Oh, can you see the full presentation? You don't need to see the. Yeah. Okay, I think I've got it. So tonight we're going to talk about two aspects of the Merauke irrigation project. This is almost going to be a 2-year project, so it's quite a complicated and intricate project. And I'm not expecting Gogo or Kania to give a full rundown of the whole project, but to prepare you, I will give a short introduction and overview. Gogo and Kania have been working with me for the last year, and I'm glad to welcome them onto the project. They will be giving more detailed talks about two very interesting aspects of the project. Gogo will speak about flood risk management and study on a proposed barrage, and Kania will speak on the water balance that she's worked on with me for the barrage, and she'll explain what a water balance is. Now, Gogo's a graduate of ITB, but he's also spent about a year or so on dam modeling and other water resource modeling, including preventing flooding and dam evaluations, breach modeling, and emergency action plans on 3 dams in East and West Nusa Tenggara. Whereas Kania has been supporting the communications and the water balance on the scheme, and she's helped with social and community development and communication materials. She's been involved in raw water supply project in NTT and NTB as a hydrologist and working on the calculation of water demand and water availability. The first slide is really the introduction, but on the right-hand side, you can see that we have 2 main resident populations on the project. We have the indigenous people shown in the top photograph, and we have transmigrants mainly from Java also on the project. In fact, there are about twice as many as the indigenous people. They're very much into a rice culture, whereas the indigenous people are more into a tuber and sago culture, and they also enjoy fishing and hunting and making crafts. Where's my next slide? All right. I'll just give you some project details. The project is called the Development of Merauke Irrigation System in Papua, Indonesia, Phase 1. The lead consultant is Euroconsult, Mott MacDonald, and they're in association with 3 local consultants whose names are on the left-hand side. The client is the Directorate of Irrigation and Lowland in the Directorate General of Water Resources. The funding is from the ADB and it's part of a program for accelerating infrastructure delivery through better engineering services project, ESP. I'm also working on several of the other projects. So where are we talking about? Well, on the left-hand side is a map of the Indonesian part of Papua, Western Papua, and on the bottom right-hand corner, which looks a bit like a parrot peeking out, is Merauke district. Now, within Merauke district, we're working in 4 sub-districts, and that's shown on the right-hand side by the pink color is where we're doing a master plan, and our area is 750,000 hectares. And below that, where most of the existing cultivation is, some of it dryland cultivation, some of it is irrigation cultivation, is a feasibility study area of 200,000 hectares. We have some important main project priorities. In our view, the priorities should be improving the farm incomes of the existing population, especially those suffering poverty. Balanced development, including identifying opportunities for indigenous people to benefit from the project. Improved irrigation and agriculture on land already cultivated. Ensuring water is available for multiple cropping. Upgrading the irrigation water management to benefit those at the ends of the schemes, because they're usually the ones that go short. And we're piloting pressure pipe irrigation for high value crops, including in Pekarangan areas between the houses. And we're introducing climate smart agriculture and supporting crop marketing, because we have to follow the whole marketing chain through to selling the products. This shows you the distribution of villages. If you look at the map, the outer map is the master plan area, and the inner map at the bottom is the feasibility study area. Can I just go back one? Okay, I think you can see the red dots on the map are the transmigration villages, and the blue dots are the indigenous villages. You can see that in the lower area, which is where we're mainly focusing on, in the center, most of the villages are transmigrants, and the blue areas are the cultivation areas around each village. Around the periphery, you'll see more of the blue dots where the indigenous people are. And through this project, we're trying to assist both sets of residents. This is sort of schematic of the project and where the work that Gogo and Kania are doing fits in. On the left-hand side, we have the master plan study, which is just coming to an end at the moment. And the first part of the master plan study is a situation analysis where we look at the existing irrigation, the existing agriculture, the existing social systems and setup, and the environment, as well as natural resources such as water and soils and land use. Below that, the master plan situation analysis report, we then have had consultations, and we're moving into the scenario developments. And we start with a without project scenario, which is the ongoing government program. If there's no loan, business as usual, and trying to assess what will happen over the next 30 years. If there was no project, because that's part of the economic analysis, is comparing the with project to the without project. The with project scenario development will be with an ADB loan. And the section underneath is the water resources strategy development. And basically, we're proposing the projects, and the agriculturalists are working with us, and so are the sociologists and environmentalists. And so far, we've developed 4 strategies for water resources development. There are large schemes. We looked at 2 of them from the 2 main rivers. We have 3 main rivers. One is the Kumbe River, one is the Merauke River, and one is the B.Eng River, where there's no real possibility of irrigation development. So we're looking at 2 large schemes there, and one of them will be the Kumbe Weir, which is a Weir-cum barrage that Kania and Gogo will talk about. Strategy 2 is pumping from rivers. Strategy 3 is that strategy 2 and 3 are really in case we can't go ahead with strategy 1, and I'll explain for reasons in a minute. Strategy 3 is we have some very large swamp areas which could store some water in the wet season and would allow us to take some of it during the dry season, but we would keep the swamps wet. And strategy 4 is their pilot schemes to test various innovations, which may be a subject for a talk a bit later in a year or so. I don't know if you can see the bottom of this screen. These studies go into a feasibility stage where we look at the economic and financial analysis of the various components. And then once we've found the most attractive schemes, they will go into detailed engineering design, which we will do the first stage of probably 4 stages covering 25,000 hectares. Okay, next slide. So the Kumbe multifunctional weir is shown on the top right-hand side. Is a drawing, looks rather like a barrage I designed in Vietnam, but it has many functions. One is that it's capable of storing an awful lot of water, and you'll see why in a minute. It will also provide irrigation, mainly by gravity, and to do that, it will raise the water level so that the canals can be higher than most of the land that's being irrigated. To assess how much irrigation area we've done, the crop water requirements and water balance that Kania will talk about. It's also very, very effective in reducing flood in the lowland areas downstream where we have the irrigation schemes, and that's where Gogo will talk about. There's also salinity control, domestic water supply. It can provide cleaner water because a lot of the water on the schemes is rather acid, and in some places it's saline. So we can also distribute water, and in the villages we will have a system for filtering the water, and it also can provide hydropower. We have 17 cumecs of environmental flow to release through the barrage, and we can release that to a hydropower system with either 1 turbine or 2 turbines. Last slide. The left-hand side shows the barrage, but it also shows the reservoir, and you can see that it's a very substantial reservoir. It goes upstream by about 70 or 80 kilometers and has several tributaries. In fact, it looks like a group of dragons fighting, but it's a very unusual shape. The barrage is shown at the bottom left-hand side. It's a purple sort of shape. And then on the right-hand side, you can see the top of the reservoir and the barrage. And then there's 2 main canals feeding a right-hand scheme called Stage 1, which covers 36,000 hectares, and a left bank scheme called Stage 2, covering 28,200 hectares. So altogether about 64,000 hectares, which is quite a large area. So that's basically my overview. You can ask me questions about it later, but we really want to focus on the more disciplined studies being done by Gogo and Kania. So I'd like to hand over to Gogo. So if we can transfer to Gogo's presentation.
Actually, Kania wants it to do first, Pak.
Yeah, I will go it first.
No problem.
Yeah. Do you all see my screen?
Yeah.
Yeah, is it bigger now?
I can see it.
Yeah, okay. At this presentation, I will speak about the irrigation water balance. At first, I think most of you know about the definition of water balance. So it is a balance of water cycle where the amount of the inflow and the outflow cycle is the same. There are 2 main parameters in the irrigation calculation. The first one is the inflow. The inflow refers to dependable discharge, and the second one is the outflow, and it is refers to the irrigation water demand. The irrigation water balance can determine the surplus or the deficit in the irrigation water system. I mean, from the water balance, we can know if the dependable discharge can meet the irrigation water demand or not. If it not, we can know how much is the deficit. At first, to analyze the inflow, the dependable flow, we must analyze the catchment area first. At this project, we want to calculate the dependable discharge at Kumbe River. This is the Kumbe River, and we want to calculate the discharge at this point between the Tanah Miring district and the Anima district. And the location is upstream of the irrigation area. This is the irrigation area. The yellow area is the catchment area and is around 3,000 kilometers square. Other than the catchment area, we have to analyze the rainfall data too. The rainfall data we get from the BMKG. It is called MOPA station. It is located here. This is downstream of the catchment area, but this is the only station that provides the good and with long time series data. It is around 30 years period of data, and it is provide the rainfall and the climate data. Next, this is the median rainfall of BMKG MOPA. From this graph, we can know that Merauke experienced a longer dry season than the wet season. The dry season happened for 7 months. It's from May until November. And the wet season happened for 5 months. It's from December until April. Other than the rainfall, the BMKG MOPA present the climatology data. There are temperature, the sunshine, humidity, and the wind speed. These all 4 parameters can be used to calculate the evapotranspiration using the Penman method. This is the result of the evapotranspiration. The maximum evapotranspiration happened at 2nd October. It is around 5 millimeter per day. And the average evapotranspiration is around 3.9 millimeter per day. After we get the rainfall and the evapotranspiration, we can calculate the dependable discharge using the rainfall to runoff modeling. At this project, we use the Fgmo method. So the MOC method is used to calculate the amount of discharge from the watershed. It is refers to water balance, where it is considered the inflow, the outflow, and the groundwater storage. The inflow refers to the inflow refers to the rainfall that come to the surface, become a surface storage, and the outflows refer to evapotranspiration and the infiltration. The infiltration will become the groundwater storage, and the surface storage and the groundwater storage will become a total runoff that will be used as the inflow in the water balance calculation. To calculate the Fgmo method, we use 4 parameters to represent the actual condition of watershed. The first one is soil moisture capacity, or SMC. Second one is processed agricultural land, or M. The third one is infiltration coefficient, E. And the last one is groundwater coefficient, K. These 4 parameters will be calibrated between the simulated discharge with the observation discharge, so it can represent the condition in the catchment area. This is the result of the simulated runoff. You can see that the discharge is very fluctuative, right? You can see at 2006, the discharge is higher than the other, and at 1997, the discharge is lower than the other. So we use the discharge with 80% probability to represent the inflow. It is in the gray line, this gray line. This is the discharge with 80% probability that will be used as the inflow for the water balance. Other than that, we use the discharge of 95% in the yellow line as an environmental flow. After we get the inflow, the dependable flow, we can continue to calculate the irrigation water demand, the NFR, the net field requirement. There are 5 factors that used to calculate the NFR. The first one is LP. So the LP is land preparation. It is water needed to prepare the irrigated land. Second one is the WLR. This is the WLR. Usually paddy will be inundated by water and must be replaced every half month. And this water that inundated the paddy will get infiltrated to the ground, and it's called percolation. The fourth one is ETC. This is the consumptive use of plants. We can calculate it by multiply the evapotranspiration with plants coefficient. And the last one is the effective rainfall. To calculate the NFR, the formula is basically quite simple. We just need to sum all the paddy demand and reduce it with the effective rainfall. The paddy demand refers to land preparation, ETC, percolation, and WLR, and we just reduce it by the effective rainfall. This is for paddy, but it's more simple in the palawija because palawija doesn't need to be inundated, so we not include the percolation, WLR, and the LP. Basically, the formula just ETC reduced by effective rainfall. This is the example of the calculation of irrigation water demand. The irrigation pattern is paddy, and palawija. This is the parameter, the effective rainfall, and this is the land preparation, and there is ETC, and percolation, the WLR, and this is the NFR that we calculate using the previous formula, and the unit is still millimeter per day, but in the calculation of irrigation water balance, we use liter per second per hectare, so we just convert the unit and then becomes a diversion requirement. Yeah, this is the NF. This is the diversion requirement. The maximum is happen at 1st June is around 1.5 liter per second per hectare. And you can see at 1st January and 1st April and 2nd November, the TR is 0. It indicates that the rainfall is enough to supply the irrigation water demand. This diversion requirement will be multiplied by the irrigation area. This is the irrigation area. In this project, we will divide the irrigation area into 2 stages. The first stage is in the red line. It is around 36,000 hectare. And the second stage is in green line. It is around 28,000 hectare. And after we get the inflow, the dependable discharge of 80% reliable flow, and then we have calculated the irrigation water demand, we can make the water balance. The blue area, represent the Kumbe 80% probability, and the bar chart represent the water demand. The blue one is for incremental flow. The yellow one is for irrigation demand for stage 2, and the green one is for irrigation demand for stage 1. You can see based on this graph that the deficit occurs from June to December, right? But in the other side, there is a surplus from January to May. There is a surplus, the excess water. So therefore, we need a reservoir to storage the water surplus, so it can be used to meet the deficit from June to December. So from the slide previously, we want to propose a barrage at the Kumbe River. The elevation is up to 10 meters, and it can make the storage this at blue area. The Indonesian area is quite large because the topography at Kumbe at Merauke is quite flat. And in this picture, I want to tell you about the storage area calculation, the storage area water balance. So the storage area water balance is important to maintain the balance of inflow and outflow, so the reservoir do not get dry. So we must know if the inflow if the outflow is larger than the inflow or not. If the outflow is larger, the reservoir will reduce every year, and it's not good. It is the outflow, the outgoing flow. It refers to irrigation water demand and environmental flow. And because there is a inundation area, there will be a losses as evapotranspiration, and we have to calculate the evapotranspiration. And the inflow is coming from the catchment area. Those illustrates it. This is the storage water balance calculation. This is the example of the calculation. The simulation of the storage water balance will be calculated every half month. This is 2nd May and 1st June, 2nd June, and the simulation start at 2nd May, and at this month, we assuming that the reservoir was full. This is the inflow, the green one is the inflow per half month, and the orange one represent the water demand. First one is irrigation water demand, evapotranspiration, environmental flow, and this is the total flow, total water demand. And there is a delta S. At this, we can see that there is a minus sign. The minus sign refers that the outflow is larger than the inflow. It means deficit. And then the positive sign, it means that the inflow is larger than the outflow. It means surplus. So this surplus will be stored to the reservoir to supply the deficit. All this value is calculated using units of volume, meter cubic, and will be converted to area, hectare, and elevation, meter, by the area storage capacity curve. And there's another thing that's important, that the elevation at the end of simulation must be returned to the initial elevation. You can see that in this calculation, at the end of simulation, the elevation is 10, same as the initial elevation. Yeah, you can see at this graph too, this is the storage elevation in the barrage. At first of simulation it's 10, and at the end it comes to 10 too. I think it's enough for me.
Yeah, thanks, Kania. That's very well presented. Thank you.
Yeah. Yeah. Gogo?
Yeah, thank you, Kania. And then I will explain about our, oh, sorry, is my Microsoft PowerPoint is restarting. Okay. Yeah. Yeah. Can you see it clearly?
Yeah,
okay.
I can.
Thank you. So this is the outline of my presentation. First, we will discuss about the input of the model, and then we will see the result of the existing condition model, and then the flood prevention with barrage or weir, and then also flood protection with weir plus dikes. And then I have an additional study about the extreme condition. So for this, I will use the U.S. Army Corps of Engineers of HECRAS, or Hydraulic Engineering Center. This is the application of you can allows you to perform one-dimensional steady flow hydraulic, two-dimensional, and then also you can make a model of bed modeling, sediment, and then water quality modeling. But for this analysis, we only I only want to explain about our two-dimensional unsteady flow river hydraulic calculation for the Kumbe and Maro rivers in Merauke. And then the input is, first of all, the river data. There is 3 input in the river data, which is cross-section data, which we got from Balai Rawa Studi in 2016, and then tides data for the downstream boundaries, and then flood discharge. It's from our hydrology team analysis. And then we've got topographic and land use from BIG, or Badan Informasi Geospasial. It's based on DEMNAS, and for land use we use BIG or Tanah Air. Actually, we also got LiDAR data, but it's just finished in this week. So yeah, maybe for this presentation, I just show you the analysis from DEMNAS. Actually, DEMNAS is not good enough actually for modeling, because DEMNAS is detecting the top of the vegetation, not the surface, not the digital surface elevation, but the terrain, the digital terrain elevation. And also the map projection of coordinate system is UTM zone 55 south. And then this is the example of river cross section. Actually, the data is quite good in MSL datum. And then this is the long section of the river. We've got 2 big river in this analysis, which is Kumbe River and Maro River. And okay, next. And this is the tides observation data that we've got from Balai Rawa Studi in 2016. It shows that the tides go around until 2 meters and decrease until -2 meters. So, and then this is the flood discharge hydrograph. We use the ASGS method for this analysis, and you can see all the return period for each river, Kumbe and Maro River. And then from this analysis, we will use the 5 years return period and 25 years return period to make a perception. And then this is digital elevation model that I've said before. This is from DEMNAS, which have a resolution of 8.25. Actually, we have a LiDAR which have a better resolution in 0.5 meters. But for this analysis, we will show you the DEMNAS, using DEMNAS analysis. And also the land use. We use this land use to recognition the mining data for the flood model. And then I will show you the existing result. Yeah. River on the top is a Kumbe River, and river on the bottom is, and the right bottom is a Maro River. And this is the result of model, the result of the model for 5 years return period, and it can make a flooded area of 23,000 hectares. And you can see actually the flooded area is massively goes into the Kumbe River. So from this point and next, we will focus on the prevention of the Kumbe River. And I will show you a video of the animation of this. Oops, yeah. This is an animation of how is flood gas. Yeah. So the Kumbe River in the top have a big impact, a massive impact of this flood. And this is for 5 years return period. Yeah. And then for the 25 return period is actually quite the same, but actually in Maro there is no massive impact on the flooded area. So this is only for 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 Kumbe only. And this is the animation for 25 years return period. So if you can see at this point, yeah, at this point, this is actually quite a low area. And from the information from the local people, actually this area is flooding every year. So it's quite makes sense to get this area get flooding. Okay. Yeah. And then we will have a look about Kumbe Barrage that actually Kania that have presentation before. We can see the impact of the Kumbe Barrage, particularly in the Kumbe rivers. Yeah, so this is the reservoir up here. And then this point here is the weir site or barrage site. And you can see the impact of the flooded area is massively decreasing due to the barrage, and the flooded area is replacing into the upstream. And actually, this area is actually a swampy area. And actually, this reservoir is filling the swamp area. Yeah. And this is for 25 years return period. You can see there's additional flooded area in here. Yeah, and then if we have another budget, we will provide to have a minor dikes or dikes in the flooded area around the Kumbe Barrage. This is the example of the flooded area this is the area that every year has been flooding, and this is the dikes to prevent additional prevention to prevent the flood. And this is the overview area of the Kumbe Barrage system and Kumbe River. Yeah, and then we have made additional study about the extreme condition. It is assumed that cyclone occurs downstream of the Merauke district and causes high wave up to 2 meters than normal. So actually, yeah, this is the result. Actually, we have a massive impact here in the city of Merauke, in the side of Maro rivers, and also the Kumbe. The impact of the cyclone. Yeah, and this is we have also massive protection of the dikes and weir to prevent those extreme conditions. So this is the result of all the model for 5 years and 25 years. You can see the flooded area is massively decreased because of the Kumbe Barrage. And then the average depth also decreased because of Kumbe Barrage. And then, yeah, you can see here that Kumbe Barrage can reduce peak flood discharge by 61% from 985 cubic meter per second into 377 cubic meter per second for condition of 5 years return period. So the impact of barrage actually quite massive for flooding. And then for 25 years return period also reducing peak flood discharge by 61% from 1,300 into 500 cubic meter per second. It's actually high impact. Yeah, actually that's all from me about the flood modeling. I will give it back to David.
Okay, thanks, Gogo, and many thanks to Kania as well. Well done. I think you've provided a very interesting talk, and hopefully we can get some questions. How do I see the questions?
In the Q&A type Pak, in the middle bottom of your screen, of your Zoom screen.
I got it. So far there's a question from Papandi, who worked with me on the flood modelling for quite a few river basins in Indonesia. So he's saying, in analysing, would you like to answer live, Papandi? Read your question live, Pandi. Okay, I can't hear him. So in analysing water balance, we get to look at river basin rather than only at the barrage alone. We have to identify the existing water users along the river. Please present the water balance in a schematic to show the water abstractions along the river. I think I can answer that, is that this is just a small part of a bigger study. And one option is to build this barrage, which will supply just about all the irrigation on either side of the Kumbe River. One of our other strategies is to provide water from existing intakes along the river that partially provide the irrigation by tidal, but in the dry season, all the farmers have to pump from the canals, and it generally leaves the farmers in the more distant areas short of water. So we are looking at pumping at these intakes as an alternative. So perhaps next time we do a presentation, we'll answer Papandi's question then, if I haven't done so already. So Phil.
Yeah, thanks David, and thanks to the presenters for a great presentation. I had a question on just time frames. So I know it's a study at this stage. What's the next step towards making this thing real? And where does the money come from to develop all that?
Well, we're hoping it's going to come from an ADB loan. We're just closing the master plan phase. We now go into a feasibility study phase. Unfortunately for this barrage, we don't have enough information upstream, so we aren't able to, because the Denmas contours have difficulty differentiating between trees and ground. We don't have that accurate a picture of the reservoir. And we also know that there are some indigenous communities that live close to the river. So we also have to identify them. And a lot of those communities are hidden by trees. So the barrage will be studied at pre-feasibility level, we hope. And then in the next phase, we're proposing that goes to detailed feasibility study and then detailed design, which will probably take about 3 or 4 years, and then there will be a 3 or 4 year construction period.
Very good. Okay, thank you.
And then Glyn's saying, whether turbines are key requirements of the design or an opportunity to provide additional benefits. Well, you've answered that in the second part. Yes, they're just additional benefits because we have to release about 16 or 17 QMEX through the river to keep the biodiversity going. And it's dropping through about 5 meters from the barrage, down from about 10 meters to 5 meters. So we think we can generate about 16 megawatts. And then Pa Akbar, who is working with me on another project, says, as we all know, the availability of data related to climate in Papua, especially in Merauke, is very limited. How do you deal with it? So perhaps Kania or Gogo can answer that.
I can answer that. Actually, for climate data, we got it from the BMKG MOPA. And actually, the data is quite good. It's provide around 30 years data, and the data is full. Yeah, it's full. Gogo, you want to add something?
Yeah, actually, the problem is the main problem is the BMKG station is outside our watershed, and yeah, maybe Dede Akbar is true that we have a limited data in Merauke, so that's the data we've got only from the BMKG data in MOPA station in the airports in Merauke.
Yeah, I'll just add that today Akbar and I were talking about the availability of data in North Sumatra for a small irrigation project up there. So it's something that's been a topic of discussion today. Are there any more? Oh, Dave, how are you? Will the barrage be an earth rock fill structure? If so, where will the rock come from? I believe Tanamera is the closest source of hard rock, although Bade may have some laterite. No, it's going to be a reinforced concrete structure, the main structure, and it'll have earth closure embankments. We still have to consider how we're going to build the embankments over the river, because I believe it's going to have very soft soils. But then when we come to that, I'll have a chat with Mike. I understand that some of the soils for the closure embankments may be available, but for the reinforced concrete, we'll have to import it. We're still discussing where we might obtain the gravel and sand. Perhaps Maluku or Sulawesi may have quarries that are suitable. Any more questions? Mike, do you want to answer yourself a question yourself? I don't hear anything. So I'm interested in the ground conditions. Isn't there a lot of peat in the part of Papua you would like to, actually, there's only a very small area of deep peat. Most of it is very shallow peat, between about half a meter. About half a meter. There is some acid sulfate in some areas, but they seem to have been successful in sluicing that, because they're growing quite reasonable crops of rice on what was acid sulfate soils. I think they're getting 4.5 tons a hectare. The high value crops we're considering in the master plan, we're considering 2 different types really. We're considering the high value crops that might be grown by the transmigrants. One opportunity I think that's in plain sight that hasn't been tried before is the irrigating the Pekarangan areas around the houses. And I think the ladies in the houses would prefer to irrigate crops around their houses than to develop new fields in swamp areas. So rather I think they'd prefer bees and butterflies and birds rather than snakes and crocodiles and mosquitoes and leeches. I put that, because we haven't been to Merauke, I couldn't put that question to some of the ladies in these resettlement and indigenous areas. But when I asked 4 of the ladies in the office whether if they were role playing as farmers' wives, would you prefer to irrigate around the house or irrigate in a swamp? I got 100% agreeing with me that around the house might be rather nicer. Yeah, the duckbill, Papandi, the duckbill weir is to try and keep the flood flow from the river in a relatively small area, because we, at the closure site, I believe the soils are far better on the hill, on the sides, than actually in the river channel. So we plan to build the barrage in a very limited space so that we don't have to excavate the hillside too much. And rather than having, say, a 300-meter wide straight weir, we can get away with a 100-meter wide duckbill barrage. It's going to be built in 2 stages. The first stage will be to 8 meters. And with that water, we can irrigate the right-hand side of the project. And then 5 years later, we may do the next stage of the barrage, which is the left bank scheme, which is 28,000 hectares. And just by raising the weir by 2 meters, we can store enough water to irrigate 28,000 hectares. So it's going to be quite an impressive barrage. With just a very, very small structure, we can store a huge amount of water from the wet season to use in the dry season. Oh, Dave, the high value crops being considered for the indigenous people are tubers, and we're also thinking of dwarf coconuts, perhaps bananas if we can make things like banana chips. But most of the crops we're thinking about are either what's the words? They're they can last either quite a long time or they can last a long time. And if they can't, they can be processed by the people into things like banana chips and other products that we hope then to be able to send to Java, Surabaya and Jakarta. Apparently quite a lot of ships come to Merauke quite heavily loaded and go back empty, which is a bit odd really, because at the moment there is so much rice being produced on the project that they can't ship it, they can't eat it all. Is there any questions on the actual flood modelling or the or on the water balance, so that Kania and Gogo can answer? Let me just see. Yeah, David, you tell me about the lemons. Yeah, we'll grow some lemons, don't worry. Yeah, I agree with you about the Pekarangan areas. But many of them, they only grow a single crop. With irrigation, they could be growing 3 crops. And I think it's a really good opportunity for the female farmers to grow nutritious crops for their families. and it will be a good way to introduce the women into the water user associations, because they're usually dominated by men. But having been part of the irrigation, I think it's a big opportunity for female farmers on these projects. Gogo, do you want to answer the question on the maximum retained water height in the weir, the barrage?
Yeah, I've done the analysis on 100 return period flow, and then it gets into 10.2 meters MSL for the maximum retained water height. And for seismic consideration, I think actually we don't we haven't made a study about the seismic and the stability of the barrage yet. But from the model, the maximum water level is around 10.2 meters, or 3 meters above the crest, or 2 meters above the crest, the weir crest.
Yeah, maybe I should answer, Pandy, because I built a very large duckbill and labyrinth weir in Vietnam, or I helped design one. And they had a lot of problems with floating bamboo at the intake and the scour channel. So I designed a floating deflector to deflect the timber around the intake and over to the weir. And when you get a flood, it would lift the water sufficiently for the logs to go over the weir. But yeah, it's a problem in any weir or barrage, and in some ways, a long duckbill weir is better than a set of gates across the whole river. Okay. We've been talking for an hour, just over an hour, and answering questions. In better days, it will be time to go and have our curry, but not this time. Phil, would you like to say something to close the meeting?
Yeah, sure. Thanks, thanks, David. And thank you both, Gogo and Kania, for taking the time to talk to us tonight. It's great to see such a large-scale project using best practice, best resources, helping the local people. It's multi-purpose and it's sustainable. It's really good to see projects like this. So often we see or read about large projects that do such damage to our environment, and this one is really in harmony with everything. So I really hope you get your funding eventually, and it goes ahead. It looks like a great project, and what a great one to be a part of in the early parts of your career. It's yeah, it's a magnificent experience. I think
at the beginning of your career or the twilight of your career.
Yeah. Both ends.
And the other thing was, I was hoping to see some questions from some of the BINUS students that might have asked Kania and Gogo about their experience of, being a student in their final year, and then 2 years later you're becoming a professional engineer.
Yep.
I thought they may be interested in that experience, but I don't see any questions.
Well, it's pretty terrifying. I'm sure Kania and Gogo will agree. Real consequences now. Anyway, thank you both for explaining your technical fields so clearly. I'm not a hydrology engineer. I could understand what you were saying, so it was very well presented, both of you, and it's great to have you both on board this evening. So with that, I think I'll hand back to Zikri to close the evening. Thank you.
Thank you, Pilwood Mensi, for your closing remarks. And thank you to Gogo Andre Benjamin and Kania Losiana for your excellent presentation. And also thank you to David Meg for guiding the session. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone. Thank you.